I had allowed as how if you wanted to have impact in the short term, you should do peer-to-peer work, and that there's a lot of really interesting problems in that space. Today I wanted to talk about a set of projects that are maybe a little longer term in that regard. You should think that you should not expect out of this that that I'm going to give you a story about how we're going to make the internet better tomorrow, or that you should expect it to be the case that this will happen tomorrow or a year from now, or even in any defined amount of time. But I think what I am going to try to convince you of is that if you have a problem with the internet, if the internet is unavailable, it is not because we don't understand how to build a better system. We actually understand the set of technologies to build a better internet, one that's at least an order of magnitude more reliable than the one we have today. And that if there are barriers to doing that, they're not technical barriers. They might be because the ISPs decide not to deploy it, or they might decide that people aren't willing to pay the money for it. But they're not technical reasons for why we can't get a better internet. So just in that context, just don't necessarily hold me to the notion of, well, how do we actually get this deployed tomorrow? That's not a question I'm going to try to answer. Okay, so what's the motivation for this? So I'm working on a project actually with Doug and also a set of other people, one of whom actually requires an insulin pump. And you might imagine that what you might want out of the internet in the future is to be able to do, outpatient monitoring. That if somebody has some medical condition, that we'd be able to put a sensor and some kind of, medical delivery process on it, such that and that's connected to some, data center where that's actually doing the application logic for it. That will actually monitor the patient and actually deliver whatever medicine is needed in the right doses and the right times. Now, the question you might ask is, would you, if you were designing such a system, there's certainly a lot of reasons for why it'd be great to be able to move patients out of the hospital and be able to have them at home or whatever. If you were going to do this, would you rely on the internet for it? Right? If you were the CIO of a medical company. Another example that was recent was a set of surgeons who were in the middle of an operating room and needed to access a patient record, and that patient record was stored in a data center, but the data center was over the internet, and so it was down. Well, it's again, if you were trying to make people build an internet that you were going to rely on for something that really mattered, as opposed to just using it for games or just using it for surfing the web or delivery of news, if it really mattered, well, now suddenly the reliability really is affected. And today, the internet doesn't have this property. You would be crazy to bet your life on whether you could get an internet connection. So that's really the question here. So for internet routing, what's odd about this is, of course, the primary design goal of the internet was this property. That is, it should be the case that if a physical path exists, we should be able to get there. So the idea is that there only one failure that the internet could have, and that would be that we have a partition. If there's no physical path, great, I can't do it. But if there's a lot of redundancy in the internet, I should be able to get it. So essentially the logic would go that if I get a physical path, I should be able to find a route. If I have a route, I should be able to get an efficient path. And if I have an efficient data path, then the data should flow. Unfortunately, none of those are true today. And so if I have a physical path, that doesn't say I have a route. Something like 10 to 15% of updates that happen on the internet, so interdomain updates, these are ones between ISPs, cause loops or inconsistent routing tables, and that these loops cause something like 90% of the packet loss in the core. Another part of this is if you ask Google, okay, what's the round trip? You can measure the round trip to their customers. They have data centers around the world, so it's not that they don't have enough data centers. They have data centers around the world, and 40% of their clients have round trip times that are enough time for you to go around the world twice. So they're clearly not finding efficient paths. And even if you have an efficient path, you can be DOSed. That is, entire countries can be DOSed, or entire companies can be DOSed, and essentially be completely removed off of the internet. So we've been doing a bunch of work to try to solve this set of problems. Oops, sorry. I'm mostly going to focus on the first couple rather than the last one just today. Okay, so one of the characteristics that I had said last time that we often do at UW, it's kind of a standard for how we go about tracking problems, is when in doubt, just start measuring things and then try to figure out from there. Here is a measurement done by one of my students who had gone off to an internship at Amazon. The question was, doing measurements, how often is it the case that Amazon sees an outage to a particular part of the internet, so to a particular prefix on the internet, and then how often does that last? So a prefix is a grouping of IP addresses that are routed in the same way on the internet. And so this is, in this case, actually a probability distribution, just to be different from all the other ones. A failure probability distribution is a function of the outage duration, and the x-axis is log scale. And so what you see about this is that there's kind of a bulge, that most of these outages that you're seeing are relatively short term, and they're being resolved faster than you would think of as human time scale. So they're resolved in 30 seconds or a minute or a couple minutes. And then there's a long tail of outages that take a lot longer. And so if we look at this kind of from a kind of quantitative perspective, 90% of these are getting resolved within a few minutes. So those are the relatively short ones. Probably no human was involved in fixing those. And what that means is that that's actually probably protocol weakness, and I'll talk about that. That'll be the first part of the talk. And the second part says that there are these long-term outages that required like human to fix. And unfortunately, those are, because they're really long, actually represent about half of the overall downtime. So if you were to try to improve the internet's reliability, you'd actually have to address both of these questions. And so the talk actually splits into two parts. One where we're going to talk about the short-term outages and how we fix them, and that are essentially how do we improve the protocols so that they can get reliable delivery. And then the second is how do we help humans go about diagnosing and fixing these long-term problems. And actually, in both cases, what we'll be able to see is that it isn't a question that you don't have a route. That is, there is a path, a physical path that connects, in most cases, a physical path that connects you to the destination, and that you're only seeing these outages because of weaknesses in the protocols or weaknesses in your operational procedures that we can improve. I should say one other thing. 2 million outages. So this was a 2-month study. So you're seeing millions of hundreds of thousands of outages a day. So these are very frequent events that are occurring. Right? They're not ones that are, there's only a few of them or so forth. The internet's reliability is about 2 orders of magnitude less reliable than the phone service, so the landline phone service today. So there's quite a bit of road for improvement. Okay, so I'm going to give you a brief primer on internet routing, so that we have the terminology correctly, and then I'll talk about the top 2 points. Half the talk will be about this kind of how do we deal with routing convergence and have high availability at these fine grains, so that's that bulge at the beginning. And then the second part is how do we build tools to be able to give high availability for these long-term events. A lot of this work appeared at NSDI. If you don't know about this conference, you should go read the proceedings. It's a great place to have kind of the practical side of networking. Okay, so how does the internet work? What's unique about the internet is it's a large-scale system built out of cooperating but competing entities. Each of these entities wants to hide the information about their operations internally. So an ISP will, in order to get traffic from one end of the planet to another, you might need to have your packets go through some sequence of ISPs on the way. Each of those ISPs potentially competes with the other ISPs on your path, but somehow is also cooperating to actually get your packets there. Each of the ISPs has an incentive to try to keep their information secret from everybody else, and so they're somehow having some coordination between them. So federation of competing elements. So you have a path through some sequence of these, and to be able to find that path, there is this thing called the Border Gateway Protocol, which is how the internet finds the path between them. The important part about this is that each network, each ISP, has its own policy that it uses for choosing its routes. And that policy is opaque in the sense that it's completely controlled by the ISP, and it doesn't need to tell anybody what the policy is. The only thing it needs to tell its neighbors is what routes it's willing to route. And so the output of the policy is visible to others, but the actual rules that it's using internally are opaque, and it's calculated only locally. So if I want to be able to get to this web server here, the routing policy will then say, okay, I'll advertise that I am the web server. I can get to the web server's ISP can get to the web server. It sends that to level 3. Level 3 tacks its own ID on the front of this and advertises those upstream. At that point, AT&T and Sprint know that they can get to the web server through L3 and will tack their ID on the front of it. And then at UW gets, oh, okay, I can get either, I can go either through AT&T or Sprint, and for one reason or another, maybe it's cheaper, maybe it has, we think it's more reliable, maybe for some other reason, you like the people at AT&T, you like the operator at AT&T. UW chooses a path that goes through AT&T. Okay, and then the traffic then flows in the opposite direction. So the advertisements come from the destination back towards the source. The actual traffic flows from the source toward the destination and follows the route that's chosen. So for in this case, if UW picked AT&T, then AT&T onward and so forth. Now in the reverse direction, the same essentially the same logic is going to apply, but there's no requirement in the internet that we use symmetric routes. So the choice of what paths to take are going to be chosen again by all of the participants in the system, but in the opposite direction. So the advertisements are going to flow now in order for me to get from the server back to the client, which would be how I send the data back from the server to the client. Then I'm going to have an advertisement from the addresses of the client back through the system, and then the server is going to pick those. And what that means is because every network can choose its own policy, you'll get these updates. Again, will propagate in the same way. L3 will say, oh, okay, in this case, I'll pick Sprint as my way of getting to the client. And so when the web server comes back, you'll have some parts of the path that'll be overlapping, some parts that will be not overlapping, and so forth. Okay, and it's just basically this consequence of building the internet out of a set of organizations. You don't have one organization running the entire internet. A set of organizations, each running with their own interests, their own commercial pressures, wanting to control exactly how they're choosing to do their own local routing. But somehow we're supposed to add this together into a global system. Okay, so that's the ISP to ISP path. In addition, I have to ask this question about how I get on the router level path between different places. And so I'll have a path that says UW needs to go to AT&T to L3 and then to the web server. If the web server is down here in Florida, well then what will happen is they'll pick some path through the sequence of routers within each of these that will get to the destination. So in this case, I might pick this route. However, often, once I've decided on a sequence of ASs, sequence of ISPs, I apologize if I use AS, I mean it's a technical term that means ISP, and I'll try to use ISP, but I'll sometimes forget. But I just mean the same thing in that case. Anyway, so I run through a sequence of ISPs, and then I'll choose, each ISP will choose the route through its ISPs to get to the next ISP that it's going to. But it can choose, often it's the case that these ISPs will peer in multiple places. They'll have multiple connections and can choose where they're going to go at these different connections. So in this case, it might choose to hop off of your local network at the closest possible point, which would be, say, San Francisco. And then, even though the red network might well need to take a longer path to get to the destination than it would be if the blue network chose a different path, a different place to enter. From the blue's perspective, hey, it's cheaper for me to go toss this traffic off quickly, so I'll toss it off at the closest point. This is sometimes called hot potato routing, and often leads to oddly shaped paths. I started getting in the work that I'm about to describe for the following problem. You might think, actually, if you look at now the path coming back from this web server, that it's actually also going to take its shortest, its optimal path as it's going backward, may well also be as badly designed as this one is, right? That only in the opposite direction. That is, it's going to actually hop up and go through Detroit rather than having to go directly in the most efficient way. And so it actually turns out that on the forward path, the forward ISP is looking like it's optimizing its traffic. And then on the reverse path, the reverse ISP is also looking like it's optimizing traffic. And the consequence of both of them is that the combination of the round trip is inefficient for both, right? It's taking a longer path than needed. And so you would think that there would be a way of getting them to agree that, well, gee, I'll take the faster path for you if you take the faster path back for me, and my customers will be happy, and we'll be happy, and everybody will be great. And we developed a set of protocols for this to happen and got no traction at all. And part of the reason is that bubble at the beginning that I showed you, which is that any time you change any router and doing anything, it's likely to cause a short-term routing convergence issue that will cause unavailability. And if your choice is either hurting availability, that is turning off connectivity for people, or slightly improving your performance or slightly improving your optimization, often people will choose the availability over the other one. So essentially, we've trained a set of network operators never to change anything about routers. Okay, so next up is this question of how do we improve this reliability? The question I'm going to try to address is, here's the algorithm that people would use, that's the algorithm in the internet, for calculating how a route will be done in this system. So the idea, as I said, there's opaque policies at each of these ISPs that adds up to the global policy. And the algorithm is this. It says, when I have something to say, right, which is I have a path that I have a path to a neighbor, and if I receive a new path, what I will do is to start using that path right away, and then I will forward that path to my neighbors with a time delay. And that time delay turns out to be really important, because otherwise, potentially, you can get an explosion of path state updates. Essentially, it's required to be able to be efficient with respect to distributing the actual path information, which turns out to be done on a essentially per group of IP address basis. Eventually, this will propagate all the information to everybody. Okay, but this algorithm, which is to say, apply the state and then propagate the state in the background, turns out to kind of necessarily involve loops. That is, necessarily involves loops. So here's an example. So in this case, I have a set of ISPs. They're connected in some topology, and they have a default set of routes. So 4 can get to 5. It has its table entry. It says, oh, okay, if I won't need to get to 5, I'll get to 5 directly. 3 says I can get to 5 through 4. But if that doesn't work, that doesn't work for some reason, I can get there through 2. Right? So 2 also says I can get to 4, and if that doesn't work for some reason, I'll get through 3. And 1, okay, I can get to 5, and if I can't, I'll go through 2. Right? And what this should mean is there's enough redundancy in the system. I could take any of the links out, and I should be able to get the traffic routed correctly. Right? It should still work. Only, right, if I run that algorithm that I had just now, what will happen is I will withdraw routes from 4. 4 will say, okay, I can't get there. Well, 4 is going to need to find an alternate route at some point. But in particular, it's going to propagate. 4 is going to withdraw its route and then propagate its its withdrawal to everyone else. Say, okay, now I can't get to 5 anymore. You need to find a different route. 2 and 3 are both going to apply the change right away and propagate the change in the background. Well, after some delay. So what they're going to do is to fall back on their second best route, which turns out to be a loop, because they're applying their state asynchronously. And then that loop will persist for however long the timeout is, and eventually they'll figure out that they had a problem and then repeat. And this is for a really simple graph. If I had a more complicated one, the convergence might actually take more than one timeout. It might actually take multiple timeouts. And so that whole bulge that I saw earlier is essentially an analogous problem to this kind of problem, right? Is causing that bulge in the output. It turns out that not only failures can cause this problem, but also policy changes. So you might imagine that I might want to say of 4 that it wants to get its traffic, instead of getting its traffic from 2 or 3, it wants to get its traffic from 6. And the reason for that, well, might be because of some internal policy constraint or some other fashion that it just wants to shift the traffic around for some internal reason. Some internal link that it's getting might be overloaded and it needs to shift the traffic around. But even just having AS4 withdraw a route and from some ISPs and not from other ones can cause a routing loop to happen. Right. And so this actually turns out to be something that ISPs really try not to do. That is interdomain traffic engineering, that is trying to optimize the network, trying to give you reasonable routes across the entire internet, tends to be something that is resisted by ISPs because it's just very difficult to get them to do it in a way that doesn't kind of undermine the reliability of the network. There's measurable behavior that the internet's reliability goes down at 8 a.m. And it's like, why is 8 a.m. a bad time? It's because operators arrive and they start doing things to routers that causes disconnectivity events that'll eventually propagate through and will resolve. And okay, that's really, like, can't we do a better job than that? Another example that somebody said was that Jen Rexford at Princeton gave the anecdote that during 9/11, immediately after, the internet's reliability went up because operators stopped typing things at router. That is, even though the large sections of routers got disconnected because of power failures, that it turned out that actually the reliability went up because people stopped actually messing with their routers. And that's nuts. I mean, this should not be the reason that we should be able to do that. This is not something that we should be able to do. So the question is, could we design a better system? And I'm going to come at this from a kind of a distributed systems perspective. And from a distributed system, you'd say, okay, what's really going on here is I have distributed state. I'm trying to update distributed state in multiple places. It needs to be consistent to be able to give you a route, an end-to-end route. And so let's apply that distributed state consistently. Now, I do need to worry about how I deal with failures. That is how I have the constraint that I want both safety, which is to say that I have a policy compliant route. If I have a policy compliant route, I'll have one, and it'll be consistently applied everywhere. But I'll also want kind of a liveness property, which is to say that I find routes quickly, and if there is a route, that I'll find it quickly. And so what I'll have is 2 separate mechanisms for dealing with these 2 different problems. But BGP achieves neither safety nor liveness because it has this, it will find these loops. That's obviously there are routes and you're not finding them, but also it's not particularly fast either because it has this these delays involved in order to keep for propagating too many updates. Okay, so 2 different mechanisms, one for liveness. The idea for liveness is to be able to dynamically route around problems quickly using known routes. So the idea is if we're shifting from known sets of states to other known sets of states, the adaptation to deal with a failure quickly ends up being relatively straightforward because you actually know that you're in a well-connected state, that you might have encountered a failure, but then you can deal with it at that point. And I will talk about that actually second. The first question is this question of safety, which is to make sure that your routing tables are actually always consistent and applied in a way that's policy compliant. So the way this is going to work is the following. Let's kind of give you a capsule version of the algorithm and then go from there. The key thing about this is that it's going to seem odd, because what's going to happen here is that I'm going to do everything exactly the same way as how BGP works, except for that I'm going to delay the application of updates. So all of the route calculation, all of the relationships that ISPs have with each other are going to be exactly the same, except for that when I need to do an update, the update's going to be delayed until it's safe to be applied. And so what that means is it's going to possibly take longer for updates to propagate, to be able to be safely applied everywhere. The other way of putting that is, if you apply them sooner, well, that could actually mean that they're going to be inconsistent for that period of time, so that's not necessarily a better thing. But we're going to delay them and only apply updates once we can know that they're actually safe and can be applied everywhere at the same time. Okay, so that's the idea. Okay, so here's a mechanism. You're going to apply BGP the way, run BGP as you did before. And one of the characteristics of this is, you might imagine that if I could send all of my changes to a central location and have it calculate everything and then tell everybody what to do, then that would be a simple solution, except it's not really consistent with how the internet works. Because I do have this notion that I want to be able to have ISPs that are companies that are cooperating together for our global routes, but that are competitive with each other. So they want to be able to have opaque policy that's completely under their control, that they're not advertising to anyone else, that they don't tell anyone, oh, well, I'm favoring AT&T over Sprint. Oh, well, then Sprint gets upset, or whatever. I mean, that you want to be able to have this notion of policy control that's completely under your own control. So you run BGP exactly as you were before, but you're simply not applying the updates immediately. So you're just changing the algorithm for applying the state change. Periodically, you take a distributed snapshot. And what's true about a distributed snapshot is essentially a global picture that's a consistent state across the entire system. What's also important to understand about this, which again, a lot of people when I give this talk, in their mind, they have the wrong picture in mind. The number of ISPs in the internet is a relatively small number. You might think of it as millions, but actually it's only there are only on the order of 3,000 ISPs that do transit in the internet. So that by transit, I mean ISPs that actually connect two other ISPs together. If you're a leaf ISP, actually you don't need to even participate in this system. You only get your routes and you never propagate them. Then everything will be fine. So Purdue is presumably a leaf ISP in this case. AT&T and Sprint and a few other places, Comcast and a few other ones like that, France Telecom, British Telecom, and so forth. Those are transit ISPs, and those are the ones that we actually care about in this setting. Okay, so you're periodically taking a distributed snapshot across these transit ISPs that tell you what updates are in transit and what ones have been completed. Anything that's in transit, any update that hasn't reached its final extent of all of the ISPs it needs to go to and has been processed at all of those ISPs, and those ISPs are ready to accomplish them, those updates are marked as incomplete. You then send this list of updates to a set of consolidators, a set of, as you would think of them as essentially the tier ones, the largest ISPs in the world, of which there are 6, that essentially serve the purpose of agreeing on the set of updates that everyone is going to apply. So these are updates that have propagated at least partially, and now I'm going to tell everybody about them, and then they tell, okay, here are the updates we're going to apply to everybody else. And now what the consolidators need to only know is what the ID number of the update is. They don't actually need to know anything more about it. So you're actually not having to propagate very much information to them, just essentially a number. It says, okay, update 567 had reached everywhere. Okay, now we get to go. Everybody can do 567 now. Okay, 543. Okay, you've now reached everywhere. Now 543 can be applied everywhere. Okay, once you've decided on this, you do need to do this in a way that's fault tolerant, which is to say that it should be tolerant to even one of the tier 1s crashing and not participating correctly. And there are algorithms that do that, so you could just use a consensus algorithm for accomplishing that. When you finally decide on the set of incomplete updates, you then propagate those to ASs. That tells you essentially each of the ASs, okay, of the updates you processed, here are the ones that are complete. Here are the ones that are incomplete, and you can apply all the complete ones. Everybody's applying all the complete ones at this point, and now we're into a consistent state that's applied synchronously everywhere. Okay? Okay, so I'd skip this notion of liveness. What do you do about the fact that it might take a while for this kind of propagation to happen? And I wanted to be able to reestablish my route quickly. The idea in the internet was essentially propagate bad news. The slogan was propagate bad news quickly. Try to apply changes quickly so that we can reestablish routes quickly. Well, we do still want to be able to recover from failures, even though we might not have a legitimate path yet, and that it might take us a little while to calculate a consistent path everywhere. So one of the solutions for this would be to dynamically route around whatever problem you had, and there are several proposals in the community for how to do this. A simple one that is a little bit impractical would be to annotate every packet that encounters a failure with the failure. And then, at that point, you would know, okay, among a set of consistent paths, I can use any path that doesn't use that failure, right? So that would give me a set of paths that I might be able to use that I would route, given that I need to find one that doesn't have this failure. Anything will do as long as it doesn't use this failed link, and that any ISP that gets a packet with one of these annotations in it would know what to do with it. But a simpler approach would be to simply tunnel your packet to a tier 1, that is to a large-scale ISP. As long as the failure, usually you'll have multiple connections to a tier 1 ISP, so even if the failure was to one of the ISPs, you'd have a connection to another tier 1 ISP. And then from there, they can take it down to wherever the destination is. Yeah.
Sometimes there are paths that will not actually go to the very top level and use some other transit.
Sorry, is the question during failures whether this would mean that?
No, in the previous slide.
Oh, in the previous slide. Yeah, no. If it's the case that the change only suppose the change only propagated to 1. Well then, I mean, if I know that I'm the only one who saw this change, then I can just apply it directly. If it propagates only to 1 and 3, then I'm using the tier 1s simply to coordinate 1 and 3 together.
But it will always go up to the tier 1, even if they do not.
Well, the update won't propagate up to them, but the coordination of the application of the update will be sent to the tier 1s. Right. Yes.
But that means that they need to know not just the ID, but also who would be expected to receive that update.
So we're assuming that they're propagating at one of these epic boundaries, that they would be propagating the set of them to all ISPs that are part of the set. So essentially you're flooding the set of consistent updates to everyone, or the incomplete list of updates, which is why it's important that they be small. Right? It's the number of updates per second is not, or per minute is not very large. And so it's not actually a lot of information that you're needing to propagate everywhere. But you're looking quizzical, so I probably didn't answer that.
I'm just wondering how much information you need to know how far that update gets propagated.
Oh no, you're just propagating it everywhere. What information do you need to know at the consolidator as to where to send this? You're just going to send it to everybody. You're going to say, here's update 567. We've now gotten information from everybody who had seen 567 that they were now complete with it, and there are no in progress messages about 567. So now we can declare it complete. Everybody who is involved in 567, you can now apply it, and I don't need I can just tell everybody 567 is now declared done, and we'll just go ahead and tell everybody that. And everybody who didn't involve 567 will just ignore it, and everybody who needed to apply it will then just apply it.
But I would know then that I'm not supposed to be involved in 567, as opposed to it not just having, it hasn't been issued yet.
Yes.
It's supposed to be involved.
Right. Right. So I'm leaking, if I don't know whether is your concern that I'm leaking extra information?
Well, I'm just concerned about, you talked about just sending the ID, and I'm wondering if I have enough, how much more information do I really need to be able to figure out?
Yeah, so I guess I'm assuming that the ISP is keeping track of the update numbers that it was involved with, and anything that it hears about that it wasn't involved with, then it would know that it didn't need to care about it. So it's only with respect to the ISP, because I can't declare it, because if the consistent snapshot is correct, then I either have a message from someone who said that they were in process. They sent me an update and I haven't processed it yet. Either the message is in flight or they haven't processed it, they haven't completed it yet. They're ready to say that it's done for them, but they haven't gotten it to me, then it's an incomplete update. And therefore, I might not have seen it yet, but if it's an incomplete update, then I'll probably, either I'll hear about this later, but nobody's going to apply an incomplete update until we've heard that it's complete. But you do want to be able to say, if the update only is in some portion of the network and doesn't involve everyone, which is most updates, that you want to be able to apply those locally quickly, as opposed to requiring every update to be propagated everywhere. Right. Okay. Okay, so this is a kind of graphical representation of this. In regular BGP, this is what happens if you get a link failure or other BGP event. And so by other BGP event, I mean a traffic engineering update or anything along those lines, or even planned outages. So one of the challenges of kind of operators for the internet is if I simply want to upgrade the operating system on a router, that can cause a BGP session reset, which is going to cause me to withdraw routes because I can't send it to this router, which will then propagate a set of inconsistent state updates through the network. So something like a planned outage should not cause any outage for reliability purposes, right? That should be just obvious in the design. But even that could potentially be a BGP event that causes an outage, right? A temporary outage. Okay, so any event causes a kind of disconnectivity for a brief period of time, either because of inconsistency or because of a failure. And over time, I'm going to, as I propagate the updates through the network, I'll slowly reestablish connectivity for everybody else. And then eventually it converges, and eventually I'm back to where I was before. And so that's actually why you see this property that you have failures that last for tens of seconds or a minute or so in kind of live settings because of this property that you propagate and eventually it gets to the destination and then you can reestablish. So for consensus routing, everything's working the same way. All the calculation of all the routes, everything is exactly the same. Everybody has exactly as much flexibility as they had before, except that when there is a failure, instead of just having this failure and having inconsistent routes, we're going to switch to this transient routing. So I'm going to redirect traffic to a tier 1. And then while that's happening, then eventually I'll take a snapshot. Maybe it hasn't propagated everywhere. At that point I can say, oh, okay, it hasn't propagated everywhere. I can't apply it anywhere yet. Eventually it will propagate everywhere. I'll take another snapshot. Maybe it's a little bit slower in this case than how I had done before, but I'm able to mask that with this kind of detour routing. And then I can apply the change because I know it's now reached everywhere, and now it can be consistently applied, and I'm back to where I had been before. So what does this mean for reliability? So I talked about what happens under failures. Let me take a simple model. We had done a wide-scale measurement study that measured every path, every visible path from any vantage point with either a Traceroute server or a Planet Lab server to anywhere, which has allowed us to map pretty much most interdomain, inter-AS relationships through the internet. So looking at that interdomain relationship, what would happen if we failed certain of these inter-AS links? So between ISP and ISP, what if some of them failed? And so let's simulate the behavior of what would happen with the BGP if we failed random links in the internet. In between ISPs and ISPs. Well, the red line is what happens there, which is the fraction of, on the x-axis, the fraction of ASs that are disconnected in that. Well, sometimes they actually, nobody gets disconnected, but often a bunch of people get disconnected, and sometimes everybody gets disconnected as a consequence of one of those failures. And so this is a cumulative fraction. And what you see with consensus routing and just the simple policy of detouring to a tier 1 is that that's almost always going to work okay. In 99.9% of the cases, there's a few cases where even the tier 1 you go to doesn't have a valid route to the destination, and therefore it can't get to the destination, even though a route actually does exist. Yeah.
In this graph, are you assuming every AS has a direct link to the tier 1 ISP?
No. This is the actual measured interdomain paths for ISPs that involve transit. So if I fail a connection where I am, so if you're Purdue, say, and you don't have multiple connections into the internet, and you fail that link, then yeah, you're offline. Right? But what should be true is if I have redundant links, if I'm an ISP and I have redundant links to them and I fail one of them, I should be able to route with what's left. It should be the case that if I have a valid path, I should find the valid path. And the algorithm is intended to do that.
I have a related question. It's that you're assuming somehow, if I am a transit ISP, I can route to the tier 1, but that may involve cost, because now I have to pay transit AS that route me to the tier 1. And I wonder if your algorithm has any flexibility to choose who I want to.
Yeah, so the mechanism for choosing, you would think of this as tunneling the tier 1 and having the tier 1 re-forward for you. And I guess we are assuming in that world that you would establish this connection, this tunnel, say, and there are various tunneling standards that people have come up with in the internet that already exist, that you would have established this tunnel in advance, that you had an existing agreement with that tier 1 to be serving as your backup path for failures. So it assumes that you're willing to pay whatever was necessary to have that happen.
But the thing is that sometimes, if you are not directly connected, if the transit AS is not directly connected to the tier 1, you kind of, yeah, you need the tunnel that
Right, you need to set that up for however many people might be in the path that would say, okay, for this connection, if I lose my connection to here for this temporary period, I can do this. If you actually look at the phone network, it has this property, which is if you have failures in the phone network, there are already existing agreements of what to do under certain failures of, oh, okay, I'm going to shift my traffic off of Sprint and into Canada in order to route around some specific failure. And so this notion of having prearranged behavior under failure conditions is actually pretty common. And at least on an operational side, it's not, that by itself is not a problem. Okay. Similarly, there are other things that are also, should actually just work, but don't in the internet. An example of this is path prepending. If I want to be able to provide a hint to the network that I would like them not to use this route, one of the ways of doing that is to add into this advertisement chain that I had shown earlier, that I would add an extra, a dummy AS at the beginning that would say, oh, this AS is longer than you thought, and therefore you should probably not use it. Right? It's essentially just a hint to say to the upstream, well, if you see longer paths, well, you shouldn't use longer paths, so it kind of is an indication that you shouldn't use a path. But even this, even introducing just a hint into the network using the existing protocols can cause temporary disconnectivity. So in general, people try to avoid it unless they really have to. The similar one goes for prefix engineering. So if I withdraw, if I have a prefix that I would like to say, I'd like to shift it from over here to over there, again, it's meant as a hint to the people who are sending traffic. They can use a different policy if they'd like, but I'd like to be able to give that hint without it necessarily disconnecting parts of the network. And so as a consequence, prefix engineering is considered deprecated. It's like you shouldn't do it because it actually has this property that will disconnect parts of it's destabilizing. And so certainly you don't want to do it unless you really, really have to, right? Unless there's just no other alternative. And one way of looking at this is how would we design the network so that it had this kind of optimization layer in it that would allow for ISPs to do kind of traffic engineering, try to get better routes without that necessarily causing disconnectivity if they were to change their policies on a kind of more regular basis. Okay, I can skip by some of this. We talked about a little bit about overhead and the delays involved, but you can imagine that this thing is reasonably efficient, not that much more inefficient than BGP is itself, and the delays are not that much more than what BGP would insert itself. Okay, if there were further questions about this, I'm going to shift to kind of the long-range part of the talk. Okay. And go through there. So as I remember, I have now talked about that side of the equation. Now this stuff, which is essentially human engineering. The problem that I'm going to try to address is this notion that the current way that we might go about troubleshooting problems on this part of the path that's the long-range path is to use this system called Traceroute. And hopefully most of you know how Traceroute works, but let me give you the quick version of it. So the idea in Traceroute is that you send a measurement packet into the network with different essentially hop counts, and at every hop it decrements the hop count, and if it gets to 0, it returns you a packet that says, oh, this is a router in your path. That's the idea. And from this, you can send a sequence of messages into the network that will tell you all of your path to a destination. The problem is, this was all designed before we had BGP, and so the problem is it only tells you the forward path, which if the reverse path looked the same as the forward path would be okay, but actually the forward path and the reverse path are potentially different. They're asymmetric. So it doesn't tell you anything about what the reverse path is doing. No information about the reverse path. So here's an example. So if you were Google and you had a client and a data center, and I had said earlier that there was these cases of clients at Google that had very long round trip times. Okay, so now you're tasked at Google with trying to fix this problem. How are you going to know what's going on? Well, one possibility that you might ask is maybe it's assigned to the wrong data center. And you would say, okay, no. You could look at the logs to be able to say that that's not the case. You could say, okay, it is actually assigned to the right data center. Okay, so the next question you might ask is the path from the data center to the client a long path? Is it going on some reasonable route? And you could do a forward trace route that you would be able to measure directly that say, oh, okay, this path is perfectly okay. It's actually traversing a path to the client that's reasonable. And then you would say, okay, what about the reverse path? Sorry, no clue. No information. Nothing that I can do. Now, you might think that the right thing to do here is, well, gee, let's just deploy a little bit of software on the client to be able to do the trace route back from the client back to the destination. The problem becomes, well, that involves installing software on clients, which means talking to Microsoft, which then essentially wedges you in, okay, no progress. So what you'd like is to be able to do this measurement without control of the client, without changing the client at all, to be able to measure what the path is from the client back to a data center. That's the goal of what we did, with the existing protocols the way they are today. You'd be able to do it without having to change a lot of stuff. That's the goal of what we're trying to do. So to be able to give you this reverse, what we're going to call a reverse trace route. And then this reverse trace route is going to give this building block for us to diagnose not only these path inefficiencies, but also be able to allow us to diagnose and fix unavailability, these long timescale unavailability problems. So I apologize if we go down this road towards how reverse trace route works, it'll pop back up to an availability issue later on. So it's essentially an understanding issue. We need to get to be able to diagnose these problems. Okay, so in the forward direction, everything's fine. We can take from the client, from the data center to the client, we can find out what the path is. But then if you were thinking, okay, how would you go about trying to diagnose from the client back to the data center? Well, what if you had a set of vantage points? Turns out the ISPs have this problem all the time, trying to diagnose their paths. So they've set up a set of a few thousand, 1,000, 1,500, something like that, vantage points around the internet where they can take trace routes from those vantage points to anywhere. And so that can give you a basis for trying to get that. So you could kind of add all of those together. And we've done this mapping structure that would say measure from all of those places to everywhere else and give you a set of paths. You can also look at those different ones and see how their paths are to a destination. And you say, okay, that's going to tell you some portion of, so you could trace to the data center in this case, that would tell you some portion of the path from the client to the data center. It wouldn't tell you all of it because unless those vantage points were precisely where the client was, that would be a problem. In the internet today, there's a few 100,000 different routable locations that actually have different routing behavior, different groups of the internet that have unique routing behavior in the internet. And so you're needing possibly to have a few 100,000 vantage points in order to be able to get a vantage point everywhere. And there just aren't that many of them. And it's pretty difficult to go get more of them. But here's a kind of observation. If we could just make a little bit of progress against this, then there's an aspect of the internet that would allow us to help. And that aspect of the internet is what's called destination-based routing, which is that whenever you're at a part of the network, the path that you're taking from that point to wherever you're going is only based on where you're going. It doesn't based on where you've come from. So you can tell what the path is from there on just from where you were. So if I can only know that R1 is on the path from D to S, then I've got a progress, because then I can ask the question, well, how do I get from R1 to there? And if I can then take another couple steps to say, okay, R1 goes to R2 and R3, and then from there, okay, how does R3 get there? And eventually I could kind of combine a sequence of steps that would allow me to know that I had reached the entire destination, right? And that I'd be able to do that. So that's the idea of what we're going to do. And now the question is, how do I get this? How do I get these segments? How do I get started on this building block in the background? And okay, this is going to seem like a hack. I mean, particularly compared to the earlier stuff that I was doing, which was like, let's design from first principles how we would build a highly reliable network. This is entirely, let's go try to abuse some aspects of the internet protocols that already exist, that routers already support, to be able to get some progress. And so I just realized that I'm not going to give you something that's going to be clean or elegant. And you could ask, and it's a reasonable question to ask, is why haven't we fixed the internet protocols to make this work better? And okay, probably Doug's a better person to answer that question than I am. It's certainly an interesting question, but our task here is to try to get this to work today as opposed to trying to get it to work elsewhere. Okay, so we're going to use this thing called the record route option, which it turns out actually has exactly what we want, which is it will measure both the forward and reverse path. That is, you send a probe and it will measure every hop on the path and every hop on the reverse path, except it's only limited to 9 hops. And in the internet, unfortunately, the average path is 15 hops. So, the average path length just in one direction is 15 hops, and the reverse path is 30. So this doesn't actually tell you very much, particularly for most connections in the internet. It's not going to tell you anything at all. So the question is, what can we use this for? Remember that we had this vantage point. We have a set of vantage points and we have a set of paths that go to them. What if we took one of those vantage points and sent it to D, but with a source address that instead of the vantage point, we send it as the source address of S. Then when D gets it, it's going to forward it to S. It's going to reply to S as if it came from S. Okay, so now if my record route starts recording, if V3 is within not 8 hops of the destination, then as it goes to the destination, it will record its route, and then as it goes back to the source, it will then reply, filling in. Say if it's within 8 hops, it will fill in 1 hop of the destination. Okay, and now we can repeat that and say, if we can find any vantage point that's within 8 hops of R1, then we can get some progress against the next step. And again, that might be a different vantage point because it might be somewhere else in the network. And then we'll go and fill in a little bit more and so forth. And we might get to the point where there is no vantage point within 8 hops of something. And so we then, again, I apologize, a hack. We use this atlas that we had calculated before that would tell us that there are some possibilities that there might be for the other hops that there is. So I could have possibly, the red line could have been the next hop, or maybe it's the yellow line could have been the next hop. Maybe it's something else that I didn't even know about, but it's possible or even likely that's probably one of those. Well, that gives us a couple possible routes that it could go through. And now if we just had a way of verifying whether R4 or R5 was on the path from the destination back to the source, we'd be okay. And it turns out there is such a thing in the internet that can you do this, and it's called the timestamp option. Again, I'm going to abuse it in ways that it wasn't intended. Which it allows for you to include a sequence of timestamps. What you want to make sure is that you're traversing R4, if it's R4, that you're traversing R4 on the path from D to S. And the way this timestamp will work is it will only timestamp if you encounter a sequence of routers in the precise order that you list them. Right? It could be with any other ones interleaved, but it has to be in that precise order. So you put in this timestamp D, and then R3, and then R4. And that can tell you that you will be encountering them in the appropriate sequence that you had intended. So that gives you a way of I'm sorry, I'd say R3 and then R4, and then that gives you a way of verifying that it's R4. And then once you've hit somebody a path that you've already measured before, then you're all off to the races, and then you're done. Okay, so that's the key idea. You're bootstrapping. There are a set of things that you have to make this work right. Routers will filter these packets. Some routers will process the options packets incorrectly. They'll do record route differently than other routers. They'll do these timestamp options differently from other routers. And that you need to be able to pick the vantage points correctly. I mean, there's a set of kind of engineering constraints to do this. But we have a deployment that you can go try out called on the reverse Traceroute website, and so now the principal question that I wanted to get to is how accurate is this? How good is it? Given that I said I wanted to deploy it correctly, in this graph it's actually an inverse cumulative distribution complement. Cumulative distribution on the y-axis, and on the x-axis it's the fraction of this traceroute hops that we've seen. So you can imagine the following measurement. We take all Planet Lab nodes and run traceroutes between them, and then ask the question, if we run reverse traceroute, how often is that accurate? Does it match the forward traceroute that we would be able to measure? And how much overlap is there? And similarly, we could ask, well, what if we just assumed that it was symmetric with the reverse with the forward traceroute, and we just did that as a simple kind of a simple one. The black line is what happens if it's symmetric. So that's the portion of the path that's actually symmetric, and you can say sometimes it's completely symmetric, and sometimes most of the time it's not completely symmetric. Sometimes it's completely different and diverges right away. So on average, you're getting not very much of the path if you assume symmetry. The red line is what we get. Which is what you get, the overlap between reverse traceroute and forward traceroute. And there are two additional things that I need to point out about this. The first is that actually because of kind of characteristics of how reverse route, record route and traceroute work, you could actually be measuring the same router but seeing different interfaces on the same router. And being able to do that resolution may mean that we are actually more accurate than this shows. And the second point, and we're not counting that for us, that is, we're counting that as an error, even if it might not be. The second point is that the coverage will improve if I have more vantage points. So if I have more vantage points that are closer to more routers, then that gives us more accuracy, and we're expecting that to happen over time. So in our case, we're getting about 87% in the median case of the reverse traceroute, which really wasn't available before. Okay, so here's an example of a path that I could debug. So in this case, it's like an actual route from Florida to Seattle that has an absurdly long round trip time. So 150 milliseconds shouldn't be anywhere close to it. It should be 50 or maybe even 60, 70, something like that. Anyway, this path basically goes from Florida. It's not actually a UW one. It's just one. It's just an IP address in Seattle. So it goes in this path, goes up to Virginia, and then goes back down to Florida, and then off to Seattle. And you might think, oh, okay, that's kind of weird. And partly the explanation for it is nobody wants to touch any routers because that causes unavailability. So they leave this kind of thing in place unless it really bothers somebody, or they may even not know that this is happening. They might not even have had anybody tell them. But at least this is diagnosable. If you have a bad route in the forward direction, you can go ask somebody you know exactly who to do that. Well, in the reverse direction, what's happening? Well, again, now you can use reverse traceroute. We run reverse traceroute, and it turns out the reverse path goes from Seattle to LA, and actually back to Seattle, and then across the country, and finally to Florida. Oops, sorry, back. And flying over Florida. And you might ask, well, why? Like, this seems weird. Why would somebody do this? Well, it turns out actually in LA, it's actually doing a peering. It's actually transiting between two different ISPs. So it's going down to LA on one ISP and coming back on a different ISP. And you might think, well, maybe they needed to go to LA in order to meet. And they didn't actually meet in Seattle. It turned out, though, that when we looked at it, they actually did have a peering point in Seattle, but they happened to be choosing the peering point in LA for doing their peering, so that then they were transiting the data all the way back again. So essentially completely nonsensical for either of the parties involved, but if they just simply didn't know that it was a problem. Okay, this is unfortunately kind of characteristic of operator struggles for this. So if I'm trying to locate failures, I have it's basically the same kind of problem, which is you'll see this kind of thing on the NANOC mailing list, so the operator mailing lists, where somebody will say, I was trying to get to level to get through level 3 in Washington, and I got lost. Things didn't get through. Can somebody help? And somebody else will mail on the mailing list, oh, okay, I tried, and yeah, I got lost in level 3, but it wasn't DC. I got lost in Denver. Okay, so now, do you have one failure? Is this two failures? Is it both Denver? Is it level 3? Is it somebody else? You have no way of knowing. And basically, from this point, you just have these forward trace routes that don't tell you anything about the reverse path. They don't tell you anything about where the real failure is, and you're kind of just stuck. So the question is, given that we have forward and reverse trace route, and we have current paths, and we also have old paths, does that give us a way of figuring out where the problem is to be able to diagnose it? So an example that we would see, or that we've seen in our this is actually a real life example that we saw in our traces of a partial failure. So a set of Planet Lab nodes that had been able to talk to USC, but then at some point became disconnected. And the question is, okay, some of them can still talk to USC and some can't. You know, this is precisely what multi-homing is supposed to deal with, except that you see many, many events that are like this, where a multi-homed customer will not be able to get round-trip communication to parts of the internet. You'll get partial disconnectivity to parts and not to other ones, right? It essentially should never happen. But what can end up happening is that there are misconfigurations or router failures where people are advertising routes. The BGP route advertisements are flowing through just fine, but the path going in the opposite direction is actually broken, and that is actually not delivering packets, and that there's really no way for the system to be able to figure this out except for some kind of diagnostic tool. So the ability to be able to group paths by where they are, okay, this will say possibly it's Cox communication that's the problem, right? Because after all, Cal State is letting stuff through and Cox isn't, but actually you don't know that, because it might be the case that there's just a common failure between those two and a reverse path, that actually they're getting through but not to the other one. So you could think, okay, well, given that we have reverse traceroute now, we could measure from the one that's working and see if we spoof to one of the other ones, and if the path gets through, then at least we now know that the reverse path is working.